Let's talk in more detail about estimating derivatives using finite differences. We might say, well, I know my current objective function value, and I might go kind of a little bit forward and compute the objective function value there, and take the difference of those, that's the difference of the y values, divide by the difference of the x values, and we call that our forward difference. When talking with Calc 1 students, I've found it helpful to talk about forward difference quotient, so they have a lower chance of forgetting to divide by the distance, the x difference. We could sometimes, if we need to, instead of going forward, we could go backward and say, I know this value, let me use a slightly smaller x value and divide by the difference of the x's. It seems like these would give you basically the same information, and that's kind of true. This one is more helpful if you're taking data that happens in real time and you know the current value of it, but you can't look forward to see what the value of it in the next minute or next hour or next day is. So you have to say, well, take the current value and a previous value. Let's take a look at the graph of what's going on here. Here's the world's best paint program. So forward difference would say, I know where my current y value is at x naught, and I'm going to find out what the new y value is, and basically compute the slope of that line. And we're saying approximate the function with that line, take its slope, and that's our estimate of the slope right here. See, it's a little shallow for the true slope. Backward difference would say take this point and this point and connect them, and you get something like that, which is a little steeper than the true function slope here. So take a sec to think about what could I do to get a better estimate of the slope of that function, which seems like it's not as steep as this one and not as shallow as that one. It might go kind of more like that. Well, you might say let's average the two. So we might say forward difference quotient plus backward difference quotient divided by 2. And that's a good idea. It's called the central difference quotient. And another way to think of it is, and if you do the algebra of adding this and this, you'll see that the f at x naught cancels because it's negative here and positive there. And so you get f at x naught plus h minus f at x naught minus h, and divide by 2h, because the 2 here and multiplies the h there. And so another way of thinking of that is we're taking a line that goes from here to there, because we're just using those two y values. Now it's interesting, that seems to not pay attention to this function value at all. It could be up here, it could be down there. It's not going to affect the slope of this estimated line. So that's something interesting to think about. It turns out, though, that central difference is a better idea because it's averaging forward and backward. You can imagine this line parallel to itself up here, kind of like that. And that is a better estimate of the slope through that point. Let's see how much better it is. Remember, I have that graph that shows us as you decrease delta x, so delta x of 10 to the negative 5, 10 to the negative 10, how much error do you get in our derivative approximation? This black curve was using the forward difference. You can see that right here, that's forward difference. But what happens if we graph the central difference quotient and its error? And we'll do that. So you can see its error decreases more quickly than forward difference does, and we get a lower overall error, so better precision, at a not so small delta x value, so that's even better. So central difference sounds great, right? What could possibly go wrong? Well, remember that we're supposing that we know the function value at x naught, and we have to evaluate the function value at x naught plus a little bit or minus a little bit. So central difference takes twice the work of forward difference. For central difference, you have to do these two function evaluations. For forward difference, you only have to do one because you already know the function value at our central point. So central difference is more precise, but also more work. It's interesting to know Excel solver computes the gradient using finite difference. It doesn't do things like power rule, exponential chain rule, product rule. So it is doing all this difference quotient stuff. there's a solver to tell it to use central differences. There's an option in solver to tell it to use central differences. So let's show that. I don't really have this set up for anything, but you see we're seeing GRG nonlinear options. There's a GRG nonlinear tab here, and you can tell it to use forward or central differences. So central gives you better steps, but they take longer. In fact, that's a general theme in thinking about optimization algorithms. Do I want to take steps that are quick to compute, but maybe not all that great, and so I might end up taking more steps, but each of them is pretty quick? Or do I want to do more care on each step and get better steps and hopefully take fewer steps to compensate for the extra time it takes? There's no obvious answer to that. It can depend on how much data you have and how hard the harder steps are and everything, but it's something to keep an eye on as we go through all these different algorithms in the future.